Jai Hind all, this is Assistant Professor Gagandeep Singh from Ajay Kumar Garg Engineering College. This is a lecture series on VLSI technology. We have discussed in the different topics in the main series. This is a complex structure, a complex topic which we need to discuss for the different perspectives. The topic is the crystal lattice structure and the defects that occur. We have discussed that there is a crystal formation which need different type of mechanisms to grow the crystal. We have also seen that there is a different type of crystals that are required for the structure of the lattice to grow a wafer or even for the epitaxial layer. So when we need a uniform crystal structure, we need to know about the crystal structure and the crystal structures available, as well as the crystal structures that are possible in the whole crystal structure defects that are possible in the whole crystal lattice. So let's see what is a crystal structure. So a crystal structure actually is a orientation or the structure of the crystal in which all the different units are oriented. For example, we have seen that when we grow a crystal, the orientation of the crystal throughout the wafer should be uniform. Even for the even throughout the lattice epitaxial layer, the whole lattice structure should have the same orientation in the crystal. So we have different type of lattices. The first the three most common or three predominant type of the lattices are simple lattices, where the atom in the lattice structure are arranged at the each corner of a unit cell. So there are four lattice atoms that make a unit cell. This lattice unit is repeated in the whole crystal structure. So this unit will make a whole crystal structure. So the orientation is a simple one, where the whole crystal will have a simple unit throughout the structure. Second is a body centered, where the body has there is some atoms which is centered at the unit cell. So this atom is at the center of the simple lattice unit. So if the 8 atoms are making a simple unit, basic unit, then this is at the middle of the structure. You can visualize it as a 3D structure, where we have a box and one atom is at the center of that box. The next one type of the structure that is needed for the our crystal growth is the face centered. Now when you imagine a box, if you imagine that box and in the face of that box, if there is some atom, for example, this is a face of this unit cell, and an atom is at this point, then this is at the face of the whole unit. Similarly, there are different faces, 1, 2, 3, 4, 5 and 6. So there are 6 atoms that are extra in this face centered lattice structure. So the simple unit cell and the face centered cell has the different kind of structures, as we can see the different arrangements of the atoms. So according to that, there are different planes which are there. One is 111 plane, which is shown by the Miller indices of the atom. Then this plane shows, then we can see with this structures, we can see that there are different structure arrangements. For the simple lattice structure, we have seen that these atoms are placed at the corners of the 4 structures only. So if we see, this has 1, 0, 0 as a Miller indices. The atom over here the structure over here has a Miller indices of 1, 0, 0. Similarly, when one atom is present over here, the atom, that plane that can be shown with the red one, will have a Miller index of 1, 1 as well as a 0. So this plane will have a Miller indices of 1, 1, 0. The third type of structure that we have discussed will have a 1, 1 as well as the 1. So this plane is at the 1, 1, 1. So the Miller indices of this one is 1, 1, 1. This Miller indices 1, 1, 1 shows that Z is equal to 1, Z is equal to 1, Y is equal to 1, that means Y is equal to 1, and X is equal to 1, that means this point. So this shows that the 3 points where the 3 ends are there. For this structure, there is X at 1, Y at 1, but Z is at 0. So we have X is equal to 1, Y is equal to X is equal to 1, Y is equal to 1, and Z is equal to 0. So these shows the coordinates of that plane, which shows the crystal structure of this crystal structure Miller indices. So for the silicon structure, we have different structures like this one. For 1, 1, 1 crystal structure means X is 1, Y is 0, Z is 0. A unit plane is with this atom, these atoms, and this is the behind this whole scene. So if we see X, Y, Z, the plane is at the 1, 0, 0. Other structure possible is there where we have one atom at the 1 position, Y position. So the other type of formation is with these atoms. This atom is behind the plane. So this atom is behind the plane. This is a 3D. So we have x-axis, we have y-axis, as well as we have z-axis. So now you can see that there is a z-axis. Z-axis is not varying, not changing. So it is x is 1, y is 1, and z is 1. The other type of structure, possible structure in the silicon, is this one, where we have 1, 1 structure. Now if in this structure we have 1 at the z, 1 at the y-axis, x-axis, and other is 1 is at the y-axis. So if we join this one, this is a triangular type of structure. So now what is the significance of knowing these structures and the structures, the Miller indexes of these structures? If we see the properties of the silicon, that depends upon these Miller indexes. If we see we have 1, 1, 1 Miller index, then we have seen that there will be more number of electrons, more number of atoms in the lattice. With having more number of atoms in the lattice, there is a higher density in the structure, higher density of atoms in the structure. This means the crystal will have more chances to collaborate with the atoms. So when they are collaborating with the atoms, they will have more, they will be easily forming the planes on the crystal. Another thing is that there are when there are no number of the atoms, that will provide a strength to the material. So the lattice structure will have the mechanical properties varying with these orientations. For example, the tensile strength is higher for this 111 Miller indices, because this will have more number of atoms in the lattice. So this lattice structure we can grow when we need a tougher material. For example, for the wafer we need a tensile material which can hold the pressure of the higher materials, as well as that for the temperature and the pressure created during the other processes. For example, lithography or the epitaxial grow and other. So we can see this is the one property that we need for the growth. Another is the another property that we can see is that with this more number of atoms, the oxidation will be more. As the number of atoms will be more, the oxidation, the possible oxidation will be more. As the number of atoms will be more, they will have more chances to gain the uh, uh, extra oxidation charge from the to form the oxidize. So 111 Miller indexes will have more oxidation than 1000 or orientation, because there are less number of atoms present on the surface. So when we will grow an epitaxial layer, this will be not preferred because of its properties. This epitaxial layer will form oxidation if we go with the 111 oxidation. So we need 100 over 11 orientation. So with this one, we can form the lattice structure, the required lattice structure for the wafer growth as well as for the epitaxial growth. Now, but there are some chances where we can have defects in the lattice. These chances are due to the misplacement or the missing of the lattice atoms. So if you can see that if this is a lattice, a basic lattice that has been formed, this has 8 atoms which are present as 1, 2, 3, 4, and behind the plane there are 4 atoms, 1, 2, 3, 4. So if these 4 atoms, if one atom is missing, then we can have a different defects that will be creating. Accordingly, we can divide these effects in the 1D, 2D, 3D defects, or we can say that it is a point defect, line defect, area defect, and the volume defects. In the point defect, there are 3 possibilities of the creation of the defects. One is that the atom is missing. For example, in the previous slide, here we have seen that if this atom is missing, this will create a lattice defect. So if this atom is not present over here, this will create a vacancy. With creation of the vacancy, the mechanical, electrical, and the mechanical properties of the atom will vary. So the crystal will behave differently with this defect. This defect is known as the vacancy, where one atom is not present in the lattice. Second is when an extra atom is present. For example, an impurity atom is present over here. So with this impurity atom to be there, it has to be come from the outside of the material. So this is known as the interstitial defects, where the extra atoms are there. Then the next defects are the Franklin defects, where which is a mixture of the vacancy as well as the interstitial defects, where one atom has left its position and it goes to the other position. So it creates vacancy defect as well as it has created an interstitial defects. So the same atom, the atom in the same lattice has shifted its position from the main position to the other position. So this will create the 2 type of the same defects in the same defect. Franklin defect will be the vacancy defect as well as the interstitial defects. So if we see the line defects, what it will create the different type of the structures in the lines. The first one is that there will be a 2D defect that will be created. For example, when this structure has missed, one atom has missed, right? It has gone to somewhere else. So this has created a vacancy. This atom has gone here, so it has created an interstitial defect. Other possibility is that this has created a Franklin defect. So now if we see, the crystal structure should have a line in its structure, but this structure is not a line. It has created some defects So this is the defect, which is defect in the line, which is not a proper line. Another possibility is that when we are heating up the crystal for the CZ method, then there is a possibility that the atom that are the layers that are coming up within this CZ method, those layers are the pasting or coming with the lower layers. So when they are forming the lower coming up with the lower layers, they may create some extra lines due to the thermal stress. This thermal stress will create this defect, which is another layer of the crystalline structure. So this crystalline structure is known as the stacking fault. So stacking fault is another fault where we are creating another other stacks in the structure. Then the 3D defects, these 3D defects can be taken as the area and the volume defects. In the area defects, we have two types, twinning and the grain boundary defects. Twinning is again a change in the orientation which makes the two parts of the crystal intermediate contacts, but they have the different orientation in the both type of the both different parts of the crystal. For example, we have seen that amorphous crystalline structures have a different different orientation in the different parts. They are not consistent. Similarly, if the whole crystalline structure is a uniform uniform structure, but if they have different parts in which two different orientations are there, then this is a twinning area defect. Another type, another possibility is that which is the grain boundary. This is due to some processing which is giving some stress to the crystalline structure. So the crystalline structure may vary in the whole structure. This variation is known as the grain boundary. So if we visualize these, structure, the twinning fault, we have this whole structure which is almost crystalline form, single crystalline form, but these two has the different crystalline forms. Here one part is the one orientation and other part is the second orientation. But if we see overall, it is a single crystalline form where the two different orientations are present. Second is the grain boundary, where grains, you can see the different parts have the different grains for the formation of the structure. In this part, the orientation is the same. In this part, the orientation is same. So this will give the different orientations in the structures. But these the range of these structures are very small. Then is the volume defects, which acts for the dislocations. Volume defect is, you can see, visualized as a 3D defect again, which occurs in the volume. For example, when there is a extra material, extra edge is present over here due to the dislocation of this material, then we will have this volume defect. This defect is more predominant where we have boundary layers or the buried layers. When we have buried layers, then the formation of the buried layer over the other layer in the CZ method or the epitaxial layer, when we grow the epitaxial layer, when the buried layer will be grown, epitaxial layer is grown over the buried layer, the buried layer will be forming some dislocations. So there are more possibilities of creation of the dislocations in the volume. Second is the edge dislocations, which are more important when we have epitaxial defects, because this will give an extra layer of the epitaxial. So here you can see that the boundary is finished over here, but the actual due to the defects, this extra layer has been formed. So when extra edge is creation, for example, when we are creating epitaxial layer, a layer is grown over the other layer. Now, when the orientation of these two layers are same, then they will be growing over each other. But if some extra material is there, orientation, for example, in 111, when the edge is out of the main atom, main Miller indices, the extra atom that is present, the atom, my finger, which is extra over the previous layer, will be formed. So with this formation of the extra material, this will give the edge, extra edge, the change in the shift in the edge. So this edge will shift, and when we will grow other layers, this edge will grow on the sideway. So this layer will form like this one. Rather, it should form rather than this formation, the edge will grow somewhat with the extra orientation. So this will give a dislocation at the edge. So this is the volume defects. So this is the lattice structure with the defects, which is required for the formation of the lattice, formation of the epitaxial layer as well as the wafer.